Welcome to our webinar today. We're going to talk about the Raspberry Pi and how to use ITK combined with VTK on the board, natively on the board. If during the webinar you have any questions, please type your questions in the question box that you will see on the GoToWebinar interface. And also we are recording the webinar, so the recording will be up in the website in a couple of days. You're welcome to visit back and replay the recording. Okay, so what we want to talk about today is the combined use of the Raspberry Pi board with some of the toolkits that we develop at Kiwi. So there is a combination of ITK and VTK that is particularly interesting on the board. In a previous webinar, we talked about the use of ITK on the board, and we focus on how to build it directly into the board. Although you could also cross-compile it if you want to build the entire toolkit. And the motivation for doing cross-compilation, of course, is that the board is relatively slow compared to the speed that you would be accustomed to in a modern desktop or laptop machine. This is a very good book about the Raspberry Pi. It's kind of the official user guide for it. It's a very good read and description of the capabilities of the system. And a little bit of history about how it came about. Why is it that there's so much interest in this little board, despite the fact that it's a relatively limited computing platform compared to what you would have in any other modern computer. And so the origins of the board are related to something that happened in Cambridge University a couple of years ago, about 5 years ago. And essentially in the computer science department, they were start noticing that they didn't have, the number of students registering for the program was diminishing, and the quality of the applicants were also diminishing, that they were arriving to the program with less experience than it used to be the case. So they were accustomed to having, in the 1990s, students that arrived to a computer science program with experience on multiple programming languages, and also some experience in hardware. So it's were students who knew how to take a desktop apart and put it back together, and probably will be able to program in C and Pascal and some other languages, maybe assembly. And towards the 2005, the nature of that background for the students was very different. So typically they were seeing students who have some background in HTML, maybe having knowing how to use Cascade style sheets. And if you were lucky, you could get a little bit of PHP programming background. And as the professors at Cambridge were looking at the reason for this change in the population, the background of the students coming in, they zero in how much experience with direct experience with programming these students were having before arriving to college. And what they were finding is that the best undergraduate students were the ones that, for one reason or another, were spending time by themselves working on programming activities. So outside of the classroom, outside of the regular and structured classes on programming. This was the students that, on their spare time, maybe as part of a hobby, maybe out of self-interest, were working directly with computers. And that kind of reconstructs the experience that many people used to have in the 80s when the first personal computers arrived, machines like the Commodore 64 or the Atari machines, or even the earlier versions of the PC or the Apple IIe, were the kind of machines that lucky teenagers will have access to. And therefore they were able to spend a lot of time, unstructured time, tinkering with the machine. And that tinkering process is probably one of the most effective ways of actually learning programming, as opposed to the structured mechanism that normally would be used in a classroom. Now, in parallel to that, there is this notion that if you were training engineering students or developing a workforce that is that has to understand how computers work, they have to have access to machines that they can take apart, put back together, decompose, and sometimes break, because only in that process they will get to understand how things work. When the students are exposed only to platforms that are closed, then they can become good users, but they are not capable of understanding how the internals of these systems work and how to take full advantage of them or how to improve them, much less how to build new ones. And so that was the motivation for this team of professors at Cambridge to develop this platform. And this evolved over a number of years. One of these professors left Cambridge and went to work for Broadcom. And in his new job, he was very familiar, or working very closely with a new generation of chips that was mostly intended for mobile devices. So ARM chips, for which the most interesting aspect is that they have very low consumption, power consumption. So these devices were gaining in computational power, remaining low consumption, and therefore it was possible to make devices for relatively small budgets. So what they decided to do was to zero into creating a computer that could be bought by a very low price, and there is a dual intent, or at least a dual intent, on sticking to that price point. And the reason is that you want students to be able to get them, and get them without having to wait until Christmas to get it. They want students to be able to break them without too much concern. So it has to be a cheap device that if you're really in the process of doing an experiment, then you just buy another one, and it's not too much of a concern. So they stick to a price line below the $50. So in this case, they put a lot of effort on looking for components that, when combined, will remain at that price point. And so that's one of the reasons when you look at the device, many things that you will expect to find in a computer are missing. For example, a case. Now, on the other hand, it's also very important that there is no case, no enclosure for this device, because it is intended to be an open board, something that will spark your curiosity. So as a user, as the person working with the board, you should all the time wondering what is it that you can do with each one of the components. Enclosing it make more of a finished product, but ones that would be less interesting for education and for training and for waking up the curiosity of the students. So the basic architecture of the Raspberry Pi is taking advantage of this ARM processor. It's a Generation 6 ARM processor. And it has a relatively small amount of memory, 512 megabytes of RAM. That's what a typical desktop used to be 10 years ago, probably. So it's very small for today's standards, but it used to be a decent computer 10 years ago, and as usually happens in the evolution of technology. The board has two USB ports. Typically, you could use them to either feed power into the board, or you could use them to connect a standard keyboard and a standard mouse. And one of the nice characteristics that it has is that the video output, you actually have two video outputs. One is an all-style composite video that you could connect to pretty much any monitor or all TV. And it also has a high-definition video output that you can also connect to modern TVs and modern projectors. So it really covers both ends of the spectrum. The motivation for using that type of connector is that the developers of the board wanted to make sure that you didn't have to buy too many other components in order to work with the board. So when you get a Raspberry Pi, you should be able to use it directly with your TV at home, or maybe an existing monitor that you may have around. You're able to use your standard keyboards and mouse that you use for any other machine. And you can also feed power to it with a standard connector, the same type of connector that most modern cell phones will use. So in that way, whoever acquires a new Raspberry Pi doesn't have to make much additional investment on getting components. The memory of the card is also using an SD card that is a pretty standard device in cameras, particularly in cameras for photography and video. So if you have any of those memory cards around, you could just reuse the one that you have, or you can buy one for a relatively low price in many places. So the philosophy of not requiring any specialized equipment to complement the board was very important. Now the board also has an audio output, the standard audio output, and it has, as an addition, a set of pins for actually running experiments. So this is well aligned, very well aligned with the purpose of the boards in the first place. They wanted to make sure that the people who were acquiring these boards to learn to work with computers, they will have access to, direct access to the hardware. So if you wanted to interface the board to create an electronic project or drive a robot, drive servos, or receive input from sensors, you can do that with a collection of 20 or so pins that are designed, are open in the air for you to use. Now the board can be found in two different models. There is model A and B. The model A is a simplified board and is intended really for projects, particularly projects that you're going to deploy and maybe leave installed somewhere. So let's say that, for example, you create a program using the Raspberry Pi that will read data from a sensor and drive open and close a door, for example, some simple electronic project. So the model A will be the kind of board that you will leave attached to that electronic project. And because it's less expensive and has less components, it would be more, it would be a better fit for you to attach to a project that you're going to essentially forget. It becomes part of that project and you can use it for a second purpose. So it's a little bit cheaper, it's $25. It doesn't have an Ethernet port because normally it's really intended for some electronic projects that you're going to deploy, not so much for being connected on the network all the time. And it has only one USB port, so pretty much a minimal setup, so you could program the board and have it deployed on the field. The Model B is more of what we described initially, and actually the one that we were showing is a Model B. So it's $35, and we'll have the standard Ethernet port and two USB ports. So the Model B is closer to a standard computer. A typical use will be that you could develop a project working in a Model B, and when you're ready to deploy it, you could transfer your code to a Model A. One of the interesting ways to do it is because the SD card, so the actual hard drive that the board is using, is this SD card that is very easy to remove. You could do all your programming on a Model B, and when you're ready, you just transfer the SD card to a Model A, and you're ready to go. There is no need to do any further adaptation. The SD card will contain the operating system itself, so it's really, essentially the hard drive of the system. This is a picture of the Model A. You can see that in the corner close to us, that's the place where the Model B will have had the Ethernet port. And beside that, on the right side, there's only one USB connector, while the Model B has two in that same location. And the rest of the board is pretty much the same. So you have still your HDMI output. So you can still do projects that can drive video output. They can drive audio output. And on the corner far from us, you will see the collection of general input-output pins. And this is the same Model B that we showed a minute ago. And this is the one that we are actually using now for the compilation of the code that we are sharing with you. Now, another interesting aspect of the Raspberry Pi and relates to the evolution of chips that are intended to be used in cell phones and mobile devices is the use of a system in a chip. So instead of having to develop a board that has a typical processor and then auxiliary chips that will do things like driving the bus, driving the input-output devices, and so on. Now, this new generation of chips have pretty much everything integrated. So the video core is inside of the chip, and the controller for the bus is inside of the chip, and the controller for devices is inside of the chip. So that's hence the reason for calling it a system in a chip. Is really an entire computer in the chip, including the RAM is also just underneath the chip when you look at the board. Now, one of the things that this particular processor has is that it has a decent video core, a GPU. Is equivalent to what PlayStation 1 will have. So, it's not a top-of-the-line today video chip, but it's a decent one that you could use for driving 3D graphics, or you could also use for driving 2D graphics, both of them. Now, because it's a mobile device, then it's using this OpenGL standard, the OpenGL ES standard, which means that the set of instructions that are available for you to interact with the 3D graphics are slightly different from what you are accustomed to see in OpenGL in desktops. And that's part of what we're going to talk today on how you take advantage of that different layer of OpenGL. So this is one of the series of blogs that we have been posting maybe starting, last year, at the end of last year. So we start with one describing the use of ITK with the Raspberry Pi, and then we follow with how to do cross-compilation, and this one in particular on how to use VTK. And one of the things that we did in this particular exercise was that we built VTK on the board. It was nice to find that we didn't need to modify the code in any way, so the compilation for the ARM processor was pretty much straightforward. It took time, but it didn't require any modification of the code. And once we have built VTK on the board, we were able to connect to the board from another computer and see the output of our rendering in the other computer. So in that particular blog post, we did it by using Ubuntu Linux laptop. And the connection between the two was done by using a secure shell. As you know, with the option X-X, you can export the graphics. So essentially all the X Windows commands, including the OpenGL commands that will do rendering for the screen, are sent to the client machine. So in this case, the client machine is the Linux laptop on the left, and the kind of server will be the Raspberry Pi that is described here on the right. The operating system that we're running in the Raspberry Pi is called Raspbian. Is a derivation of Debian. So it's essentially a Debian system, but of course compiled for the ARM processor. There's another option of operating system, or at least one other option that is very popular, that is called Occidentalis, that is distributed by the Adafruit enterprise website. Both of them work out of the box with the board. Both of them are make very easy for you to connect a wireless USB dongle into the board. So if you need to have a deployment that is using the Wi-Fi connection instead of using a wired connection on the LAN network, it's very easy to do with both of them. Okay, so in that exercise that we were doing with VTK, at the end of the exercise, we were rendering the typical holy cow, and that was done by running the X server on the Raspberry Pi, so on the server side, and then on the client side, we were running, connecting to the Raspberry Pi using SSH and exporting the X commands. And so that something that was pointed out to us just after publishing the blog, but Brad Brokamp at the National Library of Medicine, he was very kind to quickly point out that we were actually not taking advantage of the rendering capabilities of the board. We were using just the rendering capabilities of the laptop and the OpenGL that is inside that machine, and the whatever 3D capabilities that were in that particular machine. So as we were reporting, rendering speed and rendering capabilities, they were not really representing the capabilities of the Raspberry Pi. They were mostly representing the capabilities of the client machine. Now there are two parts to it, because still part of the computation actually happened on the server side, but the rendering is happening on the client side. So this, if you look at the bottom of this slide, when we have on the left the X window OpenGL in that yellow box, and on the right side we have the OpenGL ES box. So the capabilities of the video core in the Raspberry Pi were not being used in that setup. So something that we want to describe today is how you can actually make use of those capabilities. So how do you get the rendering to work directly by having access to the video core of the system in a chip? So a little bit of the architecture in the case of this system. So at the very bottom of this diagram, we have the video core. This is really the hardware. This is the GPU that is attached, is built into the processor of the system. And then above that, we have the driver. So this is the software piece. This is the driver, the device driver that talks to the video core. So this is actually one of the modifications that happen in the Raspbian Debian system, as well as the Occidentalis system, is that it contains this kernel drive. So it knows how to talk to the video core, and it will translate your system calls directly into the proper calls that interact with the hardware. Now, above that level, then we have the implementation of OpenGL ES that will be the standard API to take advantage of the graphics. Okay, let me take a look. There is a question on, can I just escape? Okay, I'm trying to look at the question. Okay, so the question in the webinar is there a plan about merging the code that has been made with VS to VTK? And they say, I think the Raspberry Pi doesn't like VTK at all because we're still relying on Mesa drivers, or is it already possible to rely on the proper GLS drivers? So the answer is yes. So you're correct in that if you use the standard VTK, so you use VTK out of the box, and this is actually what I did in that initial blog post, I was interacting with the Mesa drivers. So it was not taking advantage of the actual hardware and the video core that is in the chip. What we're going to show today is the second option that you are pointing out. So we'll talk about VES and this extension of VTK. So VES is essentially an extension for VTK that will indeed take advantage of OpenGL in mobile devices. And therefore, you will actually be able to use that rendering. So it's not really something that has to be merged with VTK the way it's done here, and it's probably the simplest way to do it is that you will download VS, and we are going to describe that in a minute, and then combine your build of VS with your build of VTK, and we do that by using the super build that is already configured when you get the project. So the final result is that you're going to end up with a compiled version of VTK in which the rendering part has been replaced with components from VES. And in addition to that, you have some components from the Kiwi platform that will make it easier for you to develop an application. So I guess the answer is it will not be really merged with VTK, but on the bright side, it doesn't really has to be merged because you can use it directly as a super build when you get the code from VES. So hopefully that answered your question, but feel free to clarify if you want me to expand more on that. Okay. Thank you for the question, by the way. All right, so we'll get back to this topic in a minute. So let's revisit how we did the configuration of ITK on the Raspberry Pi. We talked a little bit about that in our previous webinar, but just to make a refresher, so it's a little bit clearer how we are combining both of them. So you start by downloading the source code of ITK, creating a source directory for placing the code. So you can create your directory, enter into it, expand the tar.gc file that you get. And then you create another directory for doing your binary build, enter into that directory, and call ccmake. In this case, we are using ccmake that was already installed in the system. Now, because of the size of ITK and because of the limited memory that we have in the SD card, we are going to not build the entire ITK system, but we're going to take advantage of the modularized nature of ITK. So many of you may know that during the refactoring of ITK for the version 4, the toolkit was modularized, so now you can essentially turn on and off many of the pieces of the toolkit. And what we are seeing today here is one of those nice scenarios where we take advantage of that flexibility. So we don't want to build the entire system because when we build ITK with all the testing and examples enabled for all the modules, the resulting build will be close to 2 gigabytes. And we only have a hard drive here that its full size is 4 gigabytes. But already a good portion of it is taken by the system, and another portion of it is taken by the VTK build that we have on it and other packages that we have installed. So we're really working in this case with something in the order of 200 to 300 megabytes left in the system. And therefore, this functionality of ITK, as well as the functionality of VTK, because VTK is also modularized today, you could play with both of them to turn off the modules that you know that you're not going to need for your project. So things that we do directly here, we are disabling the examples because we are actually going to build a simple one. So we don't need to build all the examples that are packaged directly with the toolkit. And then we are going to use shared libraries because in that way we are going to reduce the footprint of the executables that are created. We disable the testing as well, and we are only going to keep the core module. In order to get to this window, actually, we will have to first, when we launch CCMake, one of the options that you will see as soon as you start configuring is that one of the CMake variables is called build all modules. We turn off that option, and when we do that, then we get we are presented with this new collection of groups. So ITK now has over 110, 120 modules, and they are grouped into the groups that you're seeing right now. So there is one group called filtering, another group called IO. The IO group will have all the modules, so each one of those individual modules with a particular file format, PNG, TIFF, JPEG, DICOM, and so on. And then you have groups like the registration group or the segmentation group, where inside of such groups you will find collections of registration and segmentation algorithms, respectively, grouped into modules. So typically, if you go into the segmentation group, you can find that there are currently 2 level sets modules, and inside each one of those modules there is a family of classes. So the expectation is that you will be able then to select subsets of these modules and discard the others, or not build the others. So this is one of the interesting experience that you quickly realize you have to do again with the Raspberry Pi. And it's something that we were accustomed to do in the 80s with the old computers, is that you actually have to pay attention to the size of your hard drive and think about how much you're consuming. With modern devices, we lose that habit. We know that we have a node space, and it's very inexpensive to get more space, so we tend to be very ambitious with the use of the resources. But when you look at these more limited boards, then we have to continuously pay attention to how much resources we are using. And that's part of the learning exercise. If you have a new generation of students and young people who are entering the field of computing, they should get familiarized with the use of resources, how much it takes for each one of the things that they are trying to do with the system. So the situation for us right now is that we have about 262 megabytes. This is just before we start the build of ITK. So 93% of the hard drive is already taken. Notice that it's reported actually as 3.6 gigabytes. So you start with an SD card of 4 gigabytes, you format it, you do the allocation. There already goes down to 3.6, and that's where you start loading the system, so Debian in this case, and then allocating from that level. Now, nothing prevents you from attaching an external hard drive to the board. You could perfectly use either one of the USB ports to attach a 1 terabyte hard drive to a Raspberry Pi. So it doesn't mean that you have to be stuck in the 4 gigabytes. You could also get memory cards that have more capacity. I think you can find today very easily 8 gigabytes, and I believe you can get up to 64 gigabytes in SD cards. However, if you go in that experimentation, you may want to check the Raspberry Pi website to make sure that you get a card that is compatible with the system. There is diversity in those devices, so you may want to make sure that you get one that will actually work along with the device. Okay, so after we do that selection of modules in ITK, we start the build process, and that will take 4 hours. So notice that what this represents is that there is still a lot in the core of ITK. So when you take the core of the system will be all the infrastructure for the pipelines, the image classes, some of the core of how we manage objects, exceptions, and so on. So that's the process of 4 hours. If you were attempting to build the entire ITK when we did it for the previous webinar, the time of building directly into the board, if you build testing and examples and everything, was over 4 days, and at 4 days is when we stopped building, so we actually don't know how long it will have taken. After that, we did the build using cross-compilation that was done in a laptop, and then just copied into the board. And we also did the process of building selected modules. That is probably what makes more sense when you're working directly with the board. Now, once we finish building ITK, one of the first things that we want to do is to go and compile an example. So we took one of the examples that is shipped directly into ITK. This case was the median filter. And we copy that into another directory and do the configuration. And here we're using a configuration we released, and go to the process of configuring it. And this is what we get as soon as we try to build that particular example. So we get an error that says that it doesn't find the ITK median image filter header file. And the reason for this error message is that we just enabled the core module in ITK. So we really only enabled the core module. We didn't enable the filtering module, that is where the median filter happens to be. The reason why we want to show this message is because it's a very common scenario that many of you will confront if you start using the modularization in this way. So as soon as you start disabling modules, you will run, in some cases, in situations where you're trying to use a class that is in one of the modules that you disabled. And the question, therefore, is what module is it? So the way you find that out is the following. You take that particular file that is not being found, and the reason why it's not being found in this case is that the CMake configuration of ITK only add to your search path the modules that are on, the modules that were activated during the configuration process. So because we didn't enable the modules that are in the filtering group, the path to the directories where the header files of these classes are located, those directories were not added to the search path that you will use during compilation. And therefore, when you try to look for that particular header file, the median image filter.h file, is not going to be found by the compiler. So how do we go about it? We take that particular file name, the ITK median image filter.h, and we use the locate tool. So locate is a standard system tool that is available in most Debian-derived systems. And the way it works is that you build a database with all the files in the system, and this database is typically refreshed with a cron job at some point during the night. So it's refreshed on a nightly basis. You could also update it manually by calling the command update db. And what it does is to reconstruct this list of all the files that are available in the file system. So it's extremely useful because anytime that you're looking for a particular file, you forget where this file is located, but you have an idea of what the file name is. You can call the locate command, give the name of the file or a partial name of the file, and it will come back to you with a list of locations that are good candidates, and it's a very effective, very quick way to do it. The database is built in an incremental way, so whenever you need to update it, it's not necessarily going to revisit all the disk. But there's an advantage of letting it run as a cron job that it does by default. So when we run the locate command in this case, we get back the location of two files. Notice that even though we specify the file name as ITK median image filter.h, it's still a partial match for the file that has extension .hxx. And which is a good property, so it's something that you actually want to happen. That illustrates that you could have provided only a partial file name and get a more generous search. This is useful when you are not sure of the full name of the file, or you're looking actually for a family of files, a collection or a set of files. So what is very important to look at here is that when we get this directory back, the location of the file is in the modules/filtering/smoothing. So modules is the standard directory where all the modules in ITK are located, and the next directory level, filtering level, is the group of modules, and then smoothing is the actual name of the module. So we want to, really the piece of information that we were after is the name of that module. We needed to know what is the name of the module in which this file that we are not finding is actually located. And we need that name because with it we can now go back to the configuration in ITK and enable the proper module. So we do that. We go back to the directory where we built ITK. We launch ccmake with the dot argument, and that opens again the interface, the GUI for the configuration of ITK. We go into the advanced mode that you do that by hitting the T key for toggle. So that will show you a larger collection of CMake variables, and you can search by using the / key. or you can simply scroll using the page down commands, or sorry, page up, page down keys, or the up and down, up arrow and down arrow cursors on your keyboard. So if you revisit that way the list of TMIC variables, you can get to the module underscore ITK smoothing variable. And what you do in this case is to just turn that particular module on. So by you just hitting the return key, you can turn the module on and then repeat the configuration, and you still need to rebuild. So type make again in order to recompile. It may be that not many things get recompiled. It all depends on whether the particular classes that are part of that module are implemented as .cxx files, so actual files that are contemplated, or whether they are implemented as templates, in which case it will just be compiled at the time you build your project, and there is no compilation needed on the ITK front. So we do so, we turn on that option, and now we start the make process, and it finishes in a couple of minutes. So these are only screenshots, so you don't have to wait until for the time that it will take to do this directly live on the Raspberry Pi. And then we can go back to our particular example, do make again, and this time it's going to find all the dependencies that we have for the particular project. And then we are copying one particular image file. We're copying one data set. It's a small image that is distributed along ITK, and we use it. You may have seen it a lot in the examples from the user guide, as well as the examples on the wiki and the examples that are in GitHub. So under the directory examples/data, we have a collection of images. One that we use a lot is the brain proton density slice.png image. It's a single slice of an MRI brain, or an MRI scan of a brain. So we are copying that image in this directory, and then we run the median filter just to verify that the process is actually working, and end up with this output.png file. Now, to visualize it, here is where the use of VTK combined with ITK becomes more and more interesting. So what we're showing here in this screenshot is how this looks like from the interface of the Raspberry Pi. And to make that a little bit clearer, let me show you kind of what is the setup that we are using. Okay, so this is from our camera. We have the Raspberry Pi here, and you can see that we have on the let me for a second. Okay, so this is the HDMI port on this side. Sorry, it's a bit shaky. And on this side we have mounted an USB Wi-Fi connection, and underneath we have another Wi-Fi connection. And all those cables are coming to this Atrix laptop. So this is it's essentially a DOM terminal. This is a system that was commercialized to be used along with a cell phone, the Atrix, the Motorola Atrix cell phone. The cell phone went out of the market, so you can find this relatively cheap. And it's very convenient because by attaching them together, you essentially end up with a Raspberry Pi laptop. The laptop only has, it doesn't have a circuitry, so it's just the keyboard, a battery, and the screen, but it's an HDMI screen. So it's really a perfect complement for the Raspberry Pi. So the screenshot that you're seeing in the presentation is what you will see when you're looking at the screen of the. It's a very reflective screen, so right now you won't see much there, but that's the output. The Raspbian system, and both the Raspbian and the Occidentalist systems, will be running X Windows. So what you will see is the standard desktop background of an X Windows system. It's a bit simplified because you will have less menus, but if you're familiar with GNOME or KDE, it looks very close to those. Let me extend the presentations. All right, so by using that interface, this is how we took this screenshot. So you can see that you have your typical Windows window manager. And when we go down to that particular directory, we will run the example. We can open that file and inspect the content. All right, so let's go back to the topic of VTK, and it relates to the question that one of you posted in on the webinar. So, how is all this connected? How they come along? So we essentially have the VTK that we like and love and are used to use in the desktop in the kind of Intel machines and the Macs. And the arrival of all these mobile devices and low consumption devices brought with them the use of OpenGL ES that VTK by default doesn't use. So the idea of the VES library is to make possible to use VTK, or make possible for VTK to take advantage of those platforms, or to really talk to those platforms and use their rendering capabilities. So it's essentially an extension for VTK. Now, in addition to that, there is the Kiwi platform that is an extra layer that provides classes that you will find useful when you're building an application. So, typically when you're building an application, you need to create an application class, and you need to do a little bit of interaction with the touch screens and these kind of devices. So what Kiwi provides is a collection of classes that will make easier for you to write that application. It doesn't mean that you have to use that particular set of classes, but when you're building it, you have those pre-created building blocks that makes easier, if nothing else, at least to create a prototype, but definitely create we have been used for creating actual applications that are deployed. This is the wiki page for VES, so if you're interested in learning more about the details, these are probably the best source of information. So please visit this page and get more familiar with the different layers. So the VES itself as an extension of VTK, and the Kiwi platform as a collection of building blocks or components that you can use for creating applications. And here's the website of VES, so ves.vtk.org. You will find more information there as well. The screenshots that you see on the right side are from the Kiwi viewer. I think we are going to schedule an upcoming webinar on the Kiwi viewer, so I will not go into much detail. But it's definitely a very, very interesting application. You will find that you can download it for Android devices as well as iOS devices, so iPhones and iPads. And what it does is a generic type of viewer that you can, from your mobile device, you can connect to file servers, for example, Dropbox or the Midas server at Kitware and others. So you can put your data sets in those file servers, and from your mobile devices, you can download the data set into your device and then do visualization. The Kiwi viewer will also connect to ParaView and will take advantage of the features of ParaView Web. So you can compose scenes in ParaView and then be able to see them in the Kiwi viewer. So there is a lot of material there that I'm definitely not the best person to describe it. So look forward for an upcoming webinar. And it's a very exciting development, and it's moving forward very quickly. Okay, so this shows the different layers that you have between the systems. So at the bottom level, you have OpenGL ES that is really talking on top of the drivers of the operating system. And then VES is this extension to VTK that is providing a library to make use of the rendering capabilities of OpenGL ES. And on top of that, you will have Kiwi, or the Kiwi platform, that will provide these components that make it easier for you to create your applications for Android devices or iOS devices. So if you're familiar with VTK, that most of you probably are, it has a large collection of components that do many different things. It has I/O components, data processing, mesh representation, mesh processing itself, statistical analysis, and one of the things that it does, of course, is data rendering, is visualization. And the rendering in VTK by default is using the standard OpenGL libraries that are very common in desktop and laptop devices. But then when you move into the mobile space, then that capability doesn't apply, and it's what we actually found when we did the first build of VTK on the Raspberry Pi. We were doing rendering, but we were doing it by taking advantage of Mesa, so essentially doing software rendering, not taking advantage of the actual hardware capabilities. So what VES is providing is illustrated here a little bit on the left side. So VES is providing that essentially a re-implementation of the rendering modules of VTK in such a way that they actually take advantage of the OpenGL ES capabilities of the device. So where do you get the code? This is the Git repository. It's a little bit folded, so it should be continuous. So git vtk.org vs.git. If you clone that repository, you will have the source code of the extensions. And this is distributed under the Apache license. If you recall, then VTK itself is distributed under the BSD license. So both of them give you essentially the same permissions for using them. There is no reciprocity condition, and you can use both systems for commercial applications without having to get any extra permission. So it's the same level of openness that that you get with the BSD license. ITK right now is using the Apache license as well, so it's that same level of openness. So the components that you're going to find at this level is, if you look at, so there are essentially two big pieces when you look at VS and Kiwi. On the Kiwi side, what we're illustrating here are the top. So Kiwi is built on top of VS, and VS is talking or reusing components from VTK. And the type of components that you will find in Kiwi are more of the application level. So how to load data, how to create a base class for your application, and some of the representation classes. While if you go one level below and look at the components in VS, those components in VS are really focused on the rendering part of it. So you will find a renderer, a camera, primitive mappers, viewports, kind of sister classes of the ones that are currently in VTK for doing rendering with OpenGL, with the standard OpenGL. To build the system, the most efficient way to do it is to use the super build. It's going to take long, so just as we did with ITK, it's one of those things that you want to configure, start the build, and then go and do good reading of your favorite books. So it will take several hours, just because the way it's done in the Raspberry Pi, the performance of the Raspberry Pi. An alternative option, of course, is to do cross-compilation, but then you have to set up your system for cross-compilation. So those are the two typical options. When you use the super build, what the CMake configuration of the super build is going to do is to download additional components and put them in the right directories, set up all the CMake configuration for these additional components, and build the whole in a consistent way. And so this is something that we did in this particular board. Pat Marion actually was the person who did all this configuration. So, and so Pat is very familiar with the internals of VS and was helping me to run these experiments in the Raspberry Pi. So once you have built the VS library by using the super build process, you will end up with the CMake externals directory. So you have, this is the bin/VS directory is where we built the system. The actual source code is in the home/src/VS directory. So if we go down to this particular directory and launch this test and the test Kiwi viewer and the source directory, here we are just showing again the same setup that we showed you a minute ago using the camera. So we are using the Raspberry Pi attached to the Etrix laptop. You don't have to do it this way. You could have attached directly the HDMI output of the board to a projector or your TV or any monitor that has an HDMI connection. You also find HDMI adapters to VGA and to HDMI. To DVI. So those are cover most of your options. What is sad is that some of those connectors would be as expensive as the board. You may end up paying $20 or $25 for a connector to connect to a board of $35. All right, so this is what you will see when you run that particular example. So one interesting difference here is that these examples are not going through the rendering or are not using the layers of rendering of the X Windows system in the Raspbian operating system. So this is rendering directly to the graphic board. And this is again one of those situations where for those who are learning how computers work, if you are interested in learning the actual details of operation of a computer, this brings you back to that direct connection with the hardware. That has been lost over time because systems become more and more complicated. So when you look at today a modern Linux system, there are multiple layers of software that separates you from the hardware. So by the time you're running an OpenGL application, from your actual application code down to the hardware that is actually doing the rendering, there are 3 or 4 layers in between. In this particular case, a couple of those layers have been skipped, in particular the layer of the X Windows system. So we are directly talking to the graphic board. So the way this is run here is by going directly to the terminal in the Raspberry Pi and just launching this particular executable. Now, other options that you could have consider for doing having access to these images that we're putting on the board. Another option that we showed in our previous webinar was to use the node.js system. So use node.js as a web server that will give access to the files that you're putting on the board. And the reason for considering these options is because the way the boards are used, we cannot always presume that you're going to have them as a desktop computer. So the Raspberry Pi is a good platform for deploying in the field. So it could be hanging in a roof, it could be put in a basement close to other equipment. So it will be it's very common that it will be in situations where you may not have direct access to the board or not something that you want to do on a regular basis. So it's not always attached to a monitor, it's not always attached to a keyboard where you can just log into the system. A remote system for accessing the board is something that you want to consider. So Node.js is one potential option. You could do the same with Apache. You can do the same with directly with Python. You could run a web server. And if you were to do this with Node.js, this is one very easy way to do it. You can install the Node package manager, npm, and then install this package called connect. And with this code, you can run a server by using Node.js. Essentially, write these 4 lines of code in a file, .js. If you have not worked with Node.js before, it's essentially JavaScript but run on the server side. And with the line at the bottom, you could be executing that server side. So let me then take if there are no questions, let me show you quickly how the code looks like. So here I'm logged into the Raspberry Pi. And let me show you some of the examples of VS that if you are using the rendering of VS along with ITK, this is the level at which you will have to connect images between, pass the content of an ITK image into something that you could render with VS. And probably the best example to look at, sorry, will be here. Here. By the time you go down to the SRC directory, you will see that there is a Kiwi directory, and there's just underneath that one we have the VS directory. So under VS, you will have all the classes that are doing rendering. So those are the ones that we mentioned in one of the slides. So the typical classes for doing rendering, you have a renderer, you have a camera, and so on. So they are essentially sister classes of existing functionalities in VTK, and that's how those functionalities get replaced. While if you go to the Kiwi directory, you're going to find the classes that are more oriented to be used at the application layer. So it's one level of abstraction just above that one. And then under testing, this is the application that we were running. So this is the test Kiwi viewer CPP file. So it's taking advantage of a couple of pre-created classes that will make it easier for you to run tests or actually create applications. And when you go down, let's take a quick look through it, you have the typical functionalities for managing keyboard interactions. Again, going back to the basic principles of how devices work, we have been separated from many of the basic actions or the basic interactions between the hardware and the software. So when you're using a Linux machine that has an X Windows server, or you're interacting with a Mac machine or a Windows machine. A lot of layers of software, many layers of software are connecting the physical action of hitting one key in the keyboard up to having a letter appearing on the screen. And that goes through multiple layers. In this case, some of these layers have been skipped. So, for example, this code is not using the Windows layer of communication, and so now it has to actually look at the events for the mouse, the events for the keyboard, and manage them in a more direct way. You could also, of course, manage those events through the X Windows system, but then you would be interacting with that API at a higher layer, at a higher level of abstraction. Okay, and here is, let me finish with this. This is an example of using an image. Image that is using the image data class, so the VTK image data class. Right. And the process, the structure of the code is very similar. You create an application that has the top level abstraction. It has a collection of methods. You can overload some of those methods. So if you want to define more specific behaviors, so how to manage 3D interactions, 2D interactions, how to manage the interaction, set up default views with the camera, so align with the X direction, Y direction, and so on. And at the end of it, you are going to find a main file that creates this particular class, instantiate the class, and start its processing. Okay, so I guess to summarize and to wrap up, when you want to really take advantage of the rendering capabilities of the Raspberry Pi, this is what you want to be using. You want to be using not the standard VTK build, but do it from the layer of VES. The simple way to build it is by taking advantage of the super build process. Anticipate that it's going to take several hours. You probably want to do it overnight. And then once you have it built at the VTK level, the connection between ITK and VTK can still be done through the image data class, the VTK image data class. So when done in that way, and when you render those images, you will actually be taking advantage of the rendering capabilities of the video core in the chip, as opposed to the default interaction that you would get with using Mesa as software. Okay, so if you have any questions, otherwise please remember that the webinar has been recorded and it will be posted in a couple of days, and we'll be soon organizing another one on the Kiwi viewer and VS. Thank you.